the optical spectrum of some simple molecular system within TD-DFT. I have to go faster than I have done so far. So if fail to be sufficiently clear, ask me questions in the afternoon. Okay? So let us start. We want to calculate the dynamical polarizability of the molecule, and we have already established all the building blocks, all the theoretical tools that are needed. The first one is the time-dependent Liouville equation that we want to linearize. So this equation is not linear because both the density matrix and the Kohn-Sham Hamiltonian depend on the perturbation. So this has terms that are quadratic in the perturbation and of higher order as well. So let us linearize this. You substitute rho naught plus rho prime for rho, and you drop the terms that would correspond to equilibrium, that is rho naught dot is equal to 0, as well as the commutator of H naught and rho naught is 0. So by taking this expression and linearizing it to linear order, the equation that results is the time derivative of the perturbation to the density matrix is equal to the commutator of the unperturbed Hamiltonian with the perturbed density matrix, the commutator of the unperturbed Hamiltonian with the first order perturbation to the potential, and the commutator of the external potential with the unperturbed density matrix. All of these are of linear order in the perturbation, and here I drop terms that are of second order and higher order in the perturbation. Here you have some error that is quadratic or higher order in the perturbation. Now let us see this right-hand side as some operator acting on the perturbed density matrix. Right? The commutator of H naught with rho prime is a linear operator acting on rho prime, and the exchange correlation Hartree and exchange correlation potential is a linear functional of the density matrix, and the commutator of V prime with rho naught is also linear, so this is a linear functional of a linear functional. To cut the long story short, all this brownish object here is a linear operator, super operator, acting on rho prime. That I call L as Liouvillean. I take the Fourier transform of this equation. I rho dot goes into omega, the Fourier transform of rho, and this in the frequency domain, this equation reads omega minus the Liouvillean acting on the Fourier transform of rho prime is equal to the commutator. If you have no external perturbation, then this equation has a non-vanishing solution in correspondence to the eigenvalues of this eigenvalue equation that give free oscillations of the system whose eigenvalues are excitation energies and whose eigenvectors can be used to calculate oscillator states. This is a practical way of calculating excited states within time-dependent density function theory. You calculate the Liouvillean super operator. We will see in a while how. you diagonalize it, and the eigenvalues are the excitation energies. Of course, in order to do this, you have to give an explicit representation for the density matrix and an explicit representation for the Liouvillean. The idempotency of the density matrix, that is rho square equal to rho, can be used to show, I will not show this explicitly, but it is simple to show that idempotency implies that the first order perturbation to the density matrix has a zero matrix element between occupied and virtual orbitals. So the perturbed density matrix has only matrix element between occupied and empty states, so that the density matrix response is fully characterized by these rectangular matrices whose indices are valence and conduction states. Actually, these rectangular matrices can be used to take linear combination of empty states that can be shown to be the frequency response, the response in the frequency domain of the molecular orbitals to the given perturbation. With this representation, one can build up a formula that is rather cumbersome, but is well known in the chemistry literature. For the Liouvillean, you calculate the Liouvillean in this representation, you diagonalize it, and you get the frequencies. So this approach is very good when you want to calculate individual excited states, because you have a big matrix. You can calculate one by one the eigenvalues, and this gives you easy access to individual eigenvalues, individual excitation energies. This is suitable for large matrix iterative eigenvalue solvers. Actually, this Liouvillean matrix is very large. Its dimension is equal to the number of valence states, this is the number of electrons, times the number of conduction states. It is a huge matrix. In order to diagonalize which, you have to solve large matrix iterative solvers. However, this representation of the density matrix requires the calculation of empty states that we want to avoid in general. Again, when you calculate individual response functions, for instance, the polarizability, you calculate a lot of these eigenvectors, a lot of these eigenvalues, and then at the end of the day, you end up with a miserable frequency-dependent function, and you throw away most of the information that you have calculated. Worst of all, I think, is that what can be seen as an advantage, that is the fact that this method is good for calculating individual eigenvalues. Actually, this is a drawback in all those cases where the complexity of the system is such that you are not interested in individual eigenvalues. If you have an extended system, you have a continuous spectrum, and you don't care about individual lines. Actually, all the lines are so dense that you cannot resolve all of them. And for any given frequency interval, the number of individual states that lie, the number of individual excitations that lie within a given interval increases linearly with the size of the system, right? So the larger the system, the more the states that lie into any given interval. And so this method actually is not a good one for studying very large systems, or even when you are in the continuum of small systems. If you are in the continuum of the spectrum of even a simple diatomic molecule, then in order to resolve the continuum with pseudo discrete states, a lot of work would be necessary. So that if you have a method that allows you to calculate in one step all the spectrum without calculating individual excited states, that would be much better. How to do? We go back with the linearized Liouville equation, and then we realize that the polarizability by definition is, we saw the trace of is the dipole linearly induced by some perturbation, so it is the trace of the product of the dipole operator times the density matrix response. But traces of products of operators have the mathematical properties of scalar products. So if you think in the abstract linear space of operators, you can define a scalar product in this abstract space of operators as the trace of the product of operators. Rather abstract, but if you go to think a little bit about this, you will convince yourself that this is indeed the case. So the dynamical polarizability actually is nothing but the scalar product, formally, the formal scalar product between the dipole operator and rho prime, that is the solution of this linear system. The solution of this linear system formally is the inverse of this operator on the left acting on the state on the right. So let me read this formula aloud for you. What this formula says in one sentence is that within a time-dependent density functional theory, the dynamical susceptibility of the system is such a well-defined off-diagonal matrix element of the resolvent of the Liouvillean. You calculate the Liouvillean, you calculate its Green's function, what the mathematicians call the resolvent, the inverse of the shifted operator, you calculate matrix elements and you get the polarizability. What is this good for? This is good because there are very powerful methods that allow you to calculate matrix elements of the resolvent of the operator, of an operator, without having to invert the operator, without having to calculate explicitly the The Lanczos method is the method of choice in this case, and this was introduced in our community by the group of Volker Heine in Cambridge in the 70s. And here I will describe how it works for diagonal matrix elements. For non-diagonal matrix elements, I will skip all the comments because I am way too late. So basically what the Lanczos method does, you start from the state that you want to project over the Green's function, and you define, which you call phi naught, you define a prior state as the null state, as 0, and then you set up a three-term recursion where each term of the recursion, what they call the chain, the Lanczos chain of states, is obtained from the previous two states, so the n plus 1 is obtained from the nth and n minus 1 by applying the operator to the previous one, and by taking and by defining these coefficients a and b in such a way that a is nothing but the diagonal matrix element of H, and b is defined by the condition that the vector thus generated is normalized. What is magic about this algorithm, and again I will not demonstrate this, you have to go to books in linear algebra, is that by imposing denormalization, you get orthogonality for free. So the states thus generated, these phi states, are all orthogonal among each other. So they constitute a basis for your Hilbert space. And what is even more magic is that the representation of this operator that you have used to set up the chain in the basis that thus generated is tridiagonal. So this chain is often represented in this way. You have a chain of states starting from phi naught. You have phi naught, a link to phi 1, phi 2, phi 3, and so forth. one state is linked to the next by this off-diagonal matrix element, and it has a diagonal matrix element equal to the A coefficient. The inverse of a three-diagonal matrix can be easily calculated in terms of a continued fraction. And what is to be noticed here is that all the work that you do to implement this Lanczos chain is done independent of the frequency. So this Lanczos chain does not, in the definition of the Lanczos algorithm, you don't have frequency anywhere. So the hard part of the work is independent of frequency. The frequency dependence of the Green's function, in our case of the polarizability, is basically very cheap to obtain by calculating this continued fraction that is very inexpensive to calculate once these A and B coefficients have been calculated. Okay, these can be generalized to off-diagonal matrix elements in ways that I don't have the time to go through. You will find the details in the literature that I give at the end of the presentation. Basically, in order to do this, you have to give a representation of the density matrix and of the Liouvillean, and one that does not require the calculation of virtual orbitals, of conduction states. What you do, basically, you express the density matrix as we saw in terms of these off-diagonal matrix elements, conduction and valence, and you identify the linear combinations of conduction states as the dynamical variables of your system. So instead of having as diagonal variables x these matrices that have as indices the index of the empty and the valence and the occupied states, you characterize the response by these linear combinations that you can calculate without calculating explicitly the coefficients of the linear combination. How? This is quite simple. This is the whole trick of density functional perturbation theory. Instead of calculating individual components of the response function over the conduction states, you take the function to be the most general function, in this case x and y, orthogonal to the valence manifold. You know that the most general linear combination of conduction states is equal to the most general state projected over the conduction manifold, where you have projected out the valence component. So in order to calculate the most general linear combination of conduction states, you don't have to calculate individually the conduction states. You have to take the most general function, project out the valence states, and you're done. This is the basic trick of density functional perturbation theory that can be applied in the frequency domain as well. And basically, what you have is that in terms of this representation, you can easily represent the density response in terms of these x and y functions, and you can easily represent the action of the Liouvillean and its Hermitian conjugate over the density matrix. Essentially, these products of Liouvillean times density matrix amount to the calculation of products of the unperturbed Kohn-Sham Hamiltonian times these x and y states, and to the calculation of the perturbed Kohn-Sham potential. Exactly the same ingredients as needed for time-independent density functional perturbation theory. Basically, what you have to keep in mind at this point is that the calculation of each step of the Lanczos chain requires the calculation of pairs of states, of valence states x and y, and the calculation of this pair takes twice the time as the calculation of a single iterative step of time-independent density function perturbation. So each step of Lanczos takes twice as much the time as one single iteration of a time-independent density function perturbation. On top of this, you get basically time dependence, frequency dependence for free. Beautiful. Let me skip this and let me go to some benchmark. This is the case of benzene, the spectrum of benzene calculated with a Lanczos chain of 500 steps. Remember, 500 steps is basically 500 or 1,000 steps of time-independent density functional perturbation theory, or 1,000 steps of Karp-Marinello molecular dynamics for that matter. 1,000 at low frequency, the convergence is very good. At higher frequency, it is slower, but eventually it converges to a result that coincides beautifully with what one would obtain with the real-time propagation method that I have described before, and that is totally independent. So from this Lanczos method. So two totally different approaches give the same numerical result that gives us confidence on the robustness of the implementation. In this case, the agreement with experiment is also rather good. Still, we don't want, so this number of iterations is not very large, but we want to keep it as small as possible. And in order to do this, we do a little bit of inspection, and we inspect how these A and B coefficients that are generated along the Lanczos chain depend on the iteration. You see that if you plot these coefficients as a function of the iteration index, they fall more or less on the same value. They are almost constant. They are a little bit spread, but they are almost constant, and even more, they fall into two rather distinct groups, one for even iterations, the other for odd iterations. It took a while for us to understand why this is so. We looked into the literature of the recursion method in the 70s in the group of Volker-Heine and Haydock and Kelly and stuff. Well, it can be demonstrated that the average of these values is slightly the width of basically it is the width. It is the difference between the minimum and the maximum eigenvalue of the Liouville. The minimum eigenvalue is equal to minus the maximum excitation frequency. The maximum eigenvalue is equal to plus the maximum excitation frequency. So the difference between the two is twice the maximum excitation frequency. The maximum excitation frequency is by and large given by the kinetic energy cutoff that you use for your plane wave representation. So this is more or less twice the kinetic energy cutoff, and the difference between odd and even is of the order of the optical gap. I cannot go into the detail. This is demonstrated in the literature. Take this for granted and just do some experimentation. This is the distribution of these values, again in the case of benzene, for a cutoff of 10, 20, 30, and 40, and you see that this value oscillates nicely around around 1/2 of the cutoff. So this suggests a method to extrapolate the recursion and to keep the number of terms as small as possible. What you do a small number of iterations, 100s, 200s, a few hundreds. Then you calculate the running average of these odd and even average values. And from the last iteration that you actually do, up to a very large number of several thousands or tens of thousands, you extrapolate the recursion with the running average that you have calculated. Let us see how this works. This is the case of benzene again. 1,000, 2,000, 3,000, 4,000 iterations. And here is the same result with 500, 1,000, 2,000, but these are the iterations actually done from the last iteration, that is from 500s1, from 1,000s1, from 4,000s1, up to a very large number, up to, don't know, 20,000 or 30,000. We calculate the continued fraction by extrapolating the coefficient with the running average calculated up to this number of explicitly calculated links of the chain. You see that in this particular case, with 500 iterations, you get a result that is qualitatively and even quantitatively, I would say, in very good agreement with the convergence result. So the figure to keep in mind in this case is that in the case of benzene, with 500 Lanczos chains and Lanczos steps, that is again the equivalent of 1,000 iterations of Campanello or time-independent density functional perturbation theory, you get the full TD-DFT optical spectrum. A less simple case is the case of chlorophyll. Here is the spectrum of chlorophyll calculated by TD-DFT in light blue. The experimental spectrum calculated in orange. The agreement is not perfect in this case, but you see that in this case TD-DFT is able at least to predict that the grass is green. This is an absorption peak in the blue. This is an absorption peak in the red, nothing in the green, so grass and tree leaves are indeed green as they ought to be. An even larger system. This is a dye that is present in many fruit, in the skin of many fruits and in flowers. According to the specific structure of the dye, you have different colors, and the color is the dye actually operates in wet conditions, so you have to account for water around it. This is a model for this dye that consists of 400 and something atoms. You can do a simulation, a molecular dynamic simulation, and you calculate a spectrum with Lanczos TD-DFT for different snapshots of the trajectory. You average the snapshot, and in this case, the dye would have a greenish yellowish color. In this specific case, the predicted color of the dye is some in between green and yellow. From the response function, so you can calculate where the excitation takes place, and you can visualize the excitation processes that are going on. So this is the end of the presentation. That was way longer than it ought to be. Let me thank Dario, whose PhD thesis is the basis of all the work that I have presented, and who will lead the computer lab this afternoon. Baris is at present a postdoc of ours at CISA, working on this. Ralph Gebauer, Brent Walker, Marco Saita, and Youssef Saad. Saad is a fine numerical analyst that taught us many secrets of these Lanczos chains and these numerical algorithms. Here is the original literature. As usual, the slides of the presentation can be found on my website. I will correct them, if not today, tomorrow. I'm not sure that I will be able to do this today, so don't download them today, or if you download them today, download them also tomorrow, so that you will find the corrected slides. So that's it. Thank you. I propose the following. I have I'm leaving this afternoon after the lab, so I have something practical to do for my departure. I will leave now, and I'll join you at 2 p.m. in the lab. I propose that the first 20 minutes or half an hour or whatever is needed in the afternoon is devoted to discussion. If you have questions that I am able to answer, I would be delighted to answer your questions. Then we do the lab, which will not be long. It will be a short lab this afternoon. After the lab, Nicola Marzali will lead an open session on questions on not necessarily on what we have been speaking about during the past week, but also about your current research projects and open discussion about your own work, and if we can help, if they can help, I will be away. If they can help, they will be delighted to do so. Okay? Thank you so much.